So today's focus is on polar derivatives. We are going to talk about, first of all, how you find derivatives, and then a little bit of as far as the applications. You're not going to see a ton of applications with derivatives with polar as you do with any other type of function, but there are a few certain questions that they tend to ask pretty consistently. So first, polar derivatives. When you think about polar equations, you want to think of them as like a special type of parametric equations. Since you already know how to derive parametric, it's going to make your life easier when it comes to remembering how to derive polar. So here's some formulas off the side that you should know. You're going to be given a polar equation in the form r equals some function of theta. After that, the things that you should know about how we think of x and y to kind of make it more of like a parametric. X is always going to be equivalent to r cosine theta, and y is always going to be equivalent to r sine theta. Those come from our basic unit circle and trig, but those are consistently x is always r cosine and y is always r sine. So when I take derivatives, if you think about parametric derivatives, just going to write parametric derivatives. The process for finding a parametric derivative was dy dt over dx dt. And I'm only going to talk first derivative here, so we're not going to get into kind of the messier second derivative. Now with polar, it is going to be dy d theta over dx d theta. Now here's where we get our x and our y in order to derive. So our x is going to be whatever r is, which is going to be some function of theta times cosine of theta. And our y is going to be that same function of theta times sine of theta. Now, one common theme you'll see, because these are derivatives of things that are a little more complicated, is you will often have to do a product rule to derive. Sometimes a chain rule shows up. Thankfully, very rarely do you see a quotient rule. So when you're taking the derivative, for example, of the y piece, your dy dt, you can think of it as first times the derivative of the second. So first times the derivative of the second, derivative of sine is cosine, plus second times the derivative of the first, derivative of f, we're just going to call it generically f prime, times sine of theta, messy theta, sorry. And then your dy or dx d theta, I wrote dt, I should write d theta. Got to get in the habit of putting thetas. Same thing, do a product rule with this x equation. So first times the derivative of the second, derivative of cosine is negative, so you're going to get negative f of theta sine theta, plus second times derivative of the first, which will be f prime of theta times cosine. So you can kind of generically write it. Now, to be honest, I usually don't worry about writing it this big. I try to kind of like clean it up. So I'll show you what I mean here in a second. So one other kind of special piece before I get an example here. You will at times be asked when there is a horizontal tangent to your polar function. And this actually happens a decent amount. If you think about polar functions being very circular or like looking at these cardioids, because of the way they look, you tend to have a lot more horizontal tangents and vertical tangents, because if you picture a circle, you're going to have a horizontal tangent across the top and across the bottom, and you're going to have a vertical tangent along each side. So you have a lot more opportunity to find horizontal and vertical tangents. So to find a horizontal tangent, it's going to be when the numerator of the derivative, which is the dy d theta, equals 0. But it's going to be a place that dx d theta is not 0. And then to find a vertical tangent, you need the bottom of your slope equation, which is dx d theta to equal 0. But again, it can't also make the top equal to 0. So we're often with these, we're going to use our unit circle a lot because our answers will be theta. So it might be like theta equals pi over 4, or theta equals pi over 3, or 2 pi over 3, or something like that. So let me show you an example that kind of incorporates everything that I just talked about. So we're going to start with a really simple polar equation of just sine of theta. So x, since x is r cosine of theta, then it's going to be just the r, which is sine of theta, and cosine of theta. So that's going to be your equation for the x component. You can think of it as a component. And then your y is going to be r sine theta. So you're going to have a sine and a sine, or in other words, a faster way to write it is a sine squared of theta. So now to find the derivative, so one question may just be what's dy dx, what's the derivative? You're going to find the derivative of y on top. So the derivative of this is going to be a chain rule. So power out front, power 1 less, and then the derivative of sine is cosine. So that's going to be your dy d theta. Now for your derivative of your x component, you're going to have to do a product rule. So first times the derivative of the second, derivative of cosine is negative sine, so I just put a negative out front, plus the second times the derivative of the first. Cosine times the derivative of sine is also cosine, so we get cosine times cosine, or cosine squared. And you could clean it up a little bit if you'd like. You could kind of make the bottom a negative sine squared plus cosine squared, which looks really similar to a Pythagorean identity, but it's not because of that negative. So that might be one question. Sometimes they'll say something like, whenever the angle is pi over 3, what's the slope? So you would then have to replace all your thetas with pi over 3. I will tell you, they get a little exhausting because you are plugging these angles in so many different spots and having to be comfortable with your unit circle. Or they could just say, when does it have a horizontal tangent and a vertical tangent? So that's what we're going to do. We're going to do horizontal tangent first. So horizontal tangent is when the numerator equals 0. So we're going to see what makes the numerator equal to 0. Well, that's going to equal 0 anytime sine is 0 or cosine is 0. This is also a double angle identity. You may not realize it's a double angle identity, but you could go that route as well. So sine of 0 equals 0. We're just going to go once around a unit circle. Sine of 0 equals 0 at 0. Sine of 0 also equals 0 at pi and at 2 pi. We are going to have to see what that does to the denominator. Cosine equals 0 at pi over 2 and 3 pi over 2. So if we check this, let's see. I just want to see what happens if I put 0. If I put 0 into the bottom, the sign of 0 is 0, so I get 0 plus 1. That's okay. If I put pi into the bottom, I think I'm still good. If I put pi into the bottom, if I put 2 pi into the bottom, cosine of 2 pi is the same as cosine of 0, so I have a lot of options there. 3 pi over 2, you could check that by seeing what happens if I take the sine of 3 pi over 2. 3 pi over 2. 3 pi divided by 2. Get rid of this dumb thing here. Square it and make it negative, so I end up with a negative 1. And then if I put cosine of 3 pi over 2, cosine of 3 pi over 2, and I square that, I get 0. So we're still good. So I actually have a whole bunch of places where I have a horizontal tangent. Now in the bottom, to get a vertical tangent, so vertical tangent, I'm going to set negative sine squared theta plus cosine squared theta equal to 0. This actually is also a double angle identity. You may not recognize it, so if you don't, that's not a big deal. You could also just see, when does cosine squared equal sine squared, if you don't want to mess around with other identities. So cosine squared and sine squared will be the same at pi over 4. They'll also be the same at 3 pi over 4. 3 pi over 4. I think you can also go further and say that it would be the same at 5 pi over 4 and 7 pi over 4. It really just depends on how big of an interval that you want to go. So you could have a whole bunch of places. Again, a lot of times they'll limit it, and they'll only, instead of going 0 to 2 pi, like I've seen this written as they only want to go from 0 to pi, because you do tend to have so much repetition with these that rather than have you go all the way around the unit circle, they'll just maybe look at the first half of the unit circle. So you'll see a lot of that with these horizontal and vertical, where they're very limited in what they're asking you. Sometimes they only want the first quadrant, just because you see so much repetition. One last thing to talk about, and that is something called tangent line at the pole. And I'll explain this even more in person when we're chatting. But let's say we're looking at a graph of a function that's a rose curve. You see a lot of these with rose curves. So your rose curve, this is 2 cosine 3 theta. Since there's a 3 in front of the theta, that tells you there's 3 petals. The 2 in front tells you how long each petal is. So this one, I mean, you could graph it on your calculator, but just to save you time, it kind of looks like this. Looks like that. It's this 3 petal. The petal on the right is kind of split by that polar axis, and then the other 2 are in like the second quadrant and the third quadrant. So you'll see asked sometimes, what is the tangent line at the pole? What that means, let me change colors so you can see it, is if I start right at the center at the pole, what would be a line that would be tangent to the petal? And obviously there's a whole bunch of them. There's a whole bunch of places where I could draw and have it be like flat out against the petal. So you'll see all these different things with tangent line at a pole. The way you find it, and this is going to be something that's going to really become important as we start talking about area. It's not quite as important with derivatives, but I wanted to have the beginning conversation today, is you're going to set the polar function equal to 0. If I can figure out what makes the original polar function equal to 0, I can then tell where these tangent lines at the pole are. Where is it where it's like flush up against these lines? So let's see, if I divide both sides by 2, I just get cosine of 3 theta equals 0. So now I need to think, when does cosine equal 0? Well, cosine equals 0 at pi over 2. It also equals 0 at 3 pi over 2. And you could keep going, 5 pi over 2, so on. So if I take 3 theta equal to pi over 2, divide both sides by 3, I get pi over 6. So that's actually this one. I'm going to kind of draw back over it. That is that tangent piece. I could do it again and set 3 theta equal to 3 pi over 2. Divide by 3. I end up getting just pi over 2. That is, let me make it in a different color so it stands out a little bit better. That is this tangent line. And again, you'll see there's so many possibilities. I just wanted to give you the first couple. I think the next one ends up being like 5 pi over 6, which is this one. So it's not quite on that curve. The reason that this is important is we are going to start sectioning off these pictures into regions that we can find area. And we want to know kind of where these regions lie. So if you can find this tangent line at the pole, meaning draw a ray originating at the pole so it's flush up against the graph, it's going to help that process. So we say that that is tangent line at the pole. Wanted to give you that kind of general idea before we start doing some examples in class. So that's just kind of your overall rundown. We'll do some more together, but this gives you a general idea of how to take the derivative, how to find horizontal tangents, vertical tangents, and finally tangent line at the pole.